Good morning, kids. Today we're going to learn about the logistic model for population growth. It's our last topic in differential equations, and on Friday you will have a take-home quiz on differential equations. You can start it in class, take it home to finish it, and that will be due on Tuesday of next week, and we'll start something new. So the simple model for population growth is what this logistic equation comes from. So I'm going to start with that. If you look at a simple model for population growth, with a relative growth constant, well, we've already talked about that in a roundabout sort of way in our study of differential equations. If you look at the simple model, it says that the growth of a population, dp dt, is equal to k, some constant of growth, times p, where k is equal to the growth rate as a decimal, and p is of course your population, and t is of course some unit of time. So, and of course if needed, we can always use P equals P0 e to the kt to find k, if we need to find k. Now, what we're going to do is we're going to slightly manipulate this equation so it looks like this. And I'm going to do this in a different color. All right. 1 over k, so I'm multiplying both sides by 1 over k. 1 over k times dp dt is equal to the population. That will happen each time. So the logistic model does something that we always need to do with the population. It takes into account overcrowding and death. Kind of sad, but it's realistic. So what we're looking for when we use the logistic model often is a limiting value of the population. So the relative growth rate is a linearly oops, this is not a good time for this. Okay, I'm going to have to pause because I'm frozen. Okay, I'm back. Is a linearly decreasing function of p. Where p is the population. Because if you look at this, it's going to be 1 over p times dp boy, all sorts of technical difficulties today. 1 over p times dp dt is equal to K minus A, some value A, times P. So what's happening is as our population is increasing, it's also decreasing. All right, so now if we set this equal to 0, we get the following equation. One over P dP dt equals K minus AP. And then we're going to take that and set it equal to 0. So we end up with getting K equals A times P. Or P equals K over A. Okay, so here's the thing. This is what we call the limiting value of the population, because this is the place where our rate is going to equal 0. Our rate of growth is going to end up equaling 0. All right, so that's our limiting value. That's where our population is going to level off. So let me write that down. And I'm going to have to pause, I guess. Okay, so this is the limiting value of the population. Mary's going to start crying now because everything that possibly could go wrong has gone wrong today. So what we call this, we'll call it L. That's the limiting value of the population. Also, it might be called the carrying capacity. All right. So what we're going to say is, so L, the limiting value of the population, is equal to K over A. Therefore, A, which is basically the slope of that linear function, the decreasing linear function, that's going to be equal to K over L. Right? Just doing a little algebraic manipulation of that. So what does that mean? Well, if we, and I'm going to have to go to the next page, I think this is a logical place to do that. So if we now replace A with K over L, here is what we get as a result. 1 over P dP dt, going back to our original equation, is equal to K minus, now it's not going to be K minus AP anymore. It's going to be K minus K over L times P. All right, where L, again, is that really important limiting value of the population. Now, we want to be able to take that limiting value, or what we're going to call the carrying capacity of the environment, and we want to be able to pull it right out of this logistic equation. See, once you get the logistic equation in the proper form, what happens is you can just pull that L right out of it, but it must be in the proper form to begin with. So how do we get it in the proper form? Well, First thing we're going to do is we are going to go ahead and factor the k out of this. So I'm going to get 1 over p dp dt is equal to k times 1 minus p over L. Now you've got your p in the top of that fraction, and L, which is that limiting value, which is going to be a number, is going to be in the bottom of that fraction. All right, so basically you could write it that way, or you could write it as 1 over L times P and take its reciprocal to find L. There are a bunch of different ways to do that. Well, we're not done yet, though. Now we have to multiply through by P, so we get dP dt, the rate of growth of our population, is equal to Kp times 1 minus P over L. Again, what is L? L is the carrying capacity. That's a buzzword. Lots of AP questions will ask you this, and this is one of the simplest AP questions you're going to get, because all you really need to do is isolate, make sure you get it in the form 1 minus P over L, and you will be all set. You pull that carrying capacity right out of the equation. All right, so it's the carrying capacity of the environment. And the limit as t approaches infinity of the population. So that L is very, very important. All right. So let's put that in a couple of different forms. Now, even if you don't understand the derivation, which up until this point we have just been deriving all of this, what you really need to know is how to get this in the proper form. All right, so you'll be given an equation, you need to be able to get it into this form, and then you're going to be able to pull that L right out of there. All right, so now I'm going to give you the meat of what you need to know. First thing is dP dt, and I just wrote this up above, is equal to Kp times 1 minus P over L. The other way we could say this is, let me just slide this over a bit. dP dt equals K P times 1 minus 1 over L times P. That's a subtle distinction, but what that allows you to do, if you have that 1 over L in front of the P, you can see more obviously that all you need to do is take the reciprocal of that to find L. All right, so just take 1 over that and you'll have what you need for L. All right, so now here are all the important things that you can take out of this. L is equal to the carrying capacity. If you haven't heard that word enough, I'll say it again: carrying capacity, carrying capacity, carrying capacity. And the limit of the population function as t approaches infinity. L is both of those things. It's basically, those two things are synonymous with one another. Okay, now here's some other interesting information that you need to know. The maximum growth rate, well, this is a parabola, folks. I mean, really, it's you got a p squared there, right? So the maximum of the parabola will occur at P equals L over 2. So you don't need to mess around with doing a lot of difficult math. You get this in this form, you pull out L, and you divide by 2 to find the maximum growth rate. Okay? Now, the growth rate of the population increases. Well, your p squared, if you multiply through this thing, p squared ends up being negative. So this is basically an upside down parabola, or a parabola that has a max. So what happens with a parabola that has a max? Well, it increases until you get halfway through, and then it decreases, right? So if you think about it as a parabola, the growth rate increases when 0 is less than p and p is less than L over 2. The growth rate decreases between L over 2 and L. Okay, so it's going to be going up and then going down. And then finally, the population decreases. Okay, so up till this point, we were talking about the growth rate increasing and decreasing. But the population actually starts to decrease when the growth rate becomes negative. And that's going to be after L. All right, so the population decreases after it reaches its carrying capacity. So when P is greater than L, that means your growth rate, of course, is negative. All right, so that is really all the stuff you can get out of that lovely form of the logistic equation. Then I want to give you just the solution, the overall solution to the logistic equation, which sometimes we're going to be using. And the solution is as follows. P equals L over 1 plus A e to the negative k t. Now that's just, if we solve that differential equation, that's what we would get for a solution. And this would be where A is equal to L, the carrying capacity, minus P0, the population at time 0, over P0. So again, you're going to plug right into that in order to get the solution to the logistic equation. So, having said all of that, oh look, I have the solution on the top of the next page again. I guess I can get rid of that. Today, I'm going to do a couple problems. Now, here's the tricky part of me doing a couple problems. As I have said before, I'm sort of a goof because I have no book. I did not bring home a book, and I have not been able to get there to pick up a book. So what's going to happen is we're sort of going to have to guess what the problem is. You don't have to guess, but I have to guess. And these are word problems, so that's going to be a little bit difficult for me. But I'm going to do my best. And if I do a messed up job, then you guys will have to discuss it. So you have a word problem on page 564 of your packet that you were given, the differential equations packet. We're going to look at number 2. I'm only going to assume that you are given that some population, and I'm not sure what this is a population of, perhaps it's like land, is equal to 1 over 1 plus 29.68 e to the negative 0.0275 t. The first thing they ask you in this, I'm guessing, is what is the population at time 0, or what is the initial population? That's what I would guess they're asking you in part A. So in order to figure out the initial population, you're going to plug into the formula that you're given. So at t equals 0, p would equal 1 over 1 plus 2.968 e to the 0. And then you punch that in your calculator, and you get it's equal to 0.252, or 25%. So my guess is that at this point 25% of the land is being used. Okay, so they're thinking of the land here as a population and what the carrying capacity of the land is. So at time t equals 0, 25% of the land is used. I hope I'm guessing right about this problem. The next part, I can only assume that they are asking you what the limit of the land is. So the limit as t approaches infinity of this land. So what you're going to do is you're going to plug in, you're going to take the limit as t approaches infinity of this function. Now, as t approaches infinity, this function, right, you're going to have e to the negative 0.0275 t. Well, t is getting huge, so it's e to a huge negative exponent, which approaches 0. So the limit as t approaches infinity of this function is 1. So as t approaches infinity, as the time approaches infinity, the p, the amount of the farmland that's going to be used, is 1, which would equate to, of course, 100%. So all of the land will be used for farming. The next one says, could you find out when is half of the land going to be used for farming? So we know what the equation is for the amount that's used, so we're going to take that 1 over 1 plus 2.968 e to the negative 0.025 or 0.0275 t and set it equal to 0.5. And then I'm going to erase this and rewrite it so I don't speed ahead so fast that nobody gets any of it down. I find myself going really fast. I know you can pause the video, but it's really not convenient, so let me do that for you. I'll erase this and redo it with you. So we'll multiply both sides of this by 0.5, or excuse me, by 1 plus 2.968, blah, blah, blah. So we get 1 equals 0.5 times 1 plus 2.968 e to the negative 0.0275 t. And then what we do is multiply both sides by 2 to get rid of the 0.5. So we get 2 is equal to 1 plus 2.968 e to the negative 0.0275 t. This is pretty easy to solve, right, kids? And then you subtract 1, so you get 1 equals 2.968 e to the negative 0.0275 t. So then we get 1 over 2.968 equals e to the negative 0.0275 t. Taking the natural log of both sides, we get the natural log of 1 over 2.968 equals the natural log of that, which just yields negative 0.0275 t. Dividing by negative 0.0275, and you get t equals 39.6 years. So half of the land will be used after 39.6 years. Now, what does that mean? Well, what was L equal to? Well, the limit of our function, remember, in part B, we took the limit of our function, right? We found it to be 1. L is equal to 1 here. That's what we got out of that, right? That's the same thing. Taking the limit of the function is the same thing as pulling that L out of the derivative of the function, right? So both will work. This asks, when is the population growth, when is the dp dt the greatest, all right? So when is the land being used at the highest rate? So dp/dt is greatest at p equals L over 2. So since L was equal to 1, and that's up there, you found that up there in part B. Then P would be equal to 1/2. Okay, so the growth, or the rate at which the land is being used, is greatest at P equals 1/2, which occurs after 39.6 years, according to part C, because in part C we actually set P equal to 1/2, right? So, and we have figured that out already, so it would occur in 1974. Now, I know that was a crazy problem, kids. I'm sorry I don't have that book in front of me, but I think if you're looking at the problem, you should be able to figure out what just happened there. Number 8 is a little more straightforward. It's not to say that I know what the exact problem is, again. In number 8, you have, I always like to write those at the top of the page. You're going to have to, of course, memorize them for the AP exam, but I mean, writing them at the top of the page right now will help you to memorize them. Those two things, very, very important to know. All right, so please commit them to memory. What I'm going to do when I get back is every day you're going to have a quiz on some sort of information that you need to know. I'm going to put it on the board. I'm going to make you write stuff down in that quiz, because I think that's the only way you're going to memorize all the information you need to memorize. I've tried many ways in the past and it just never works. I just need to make you memorize. Because honestly, half of this exam will be the memorization. Alright, so going on, I digressed. Going on to number 8, we're given in number 8, dp, I can only assume we're given dp dt is equal to 0.25 p times 1 minus 0.0004 p. And in this problem, I'm thinking that we're asked to find the carrying capacity of this population. Alright, so this is already in pretty good form. You may want to rewrite 0.0004 as a fraction, or you could just, divide 1 by it, and you're going to find what the carrying capacity of the population is. All right, I'm going to write it as this: dp dt equals, you know how I'm partial to fractions, so 0.25p times 1 minus 1 over 2500. If you write that as a fraction, it's 1 over 2500 times p. So what is L? What is the limiting value of the population, or the carrying capacity of the population? Well, you can see it. It's the reciprocal of whatever occurs in front of p when you have the equation in this form right here. So L is equal to 2500. And then they must also ask you in this for K, I think. K in this, of course, is your constant, right? The form is K times P, so your constant here is 0.25. So the limiting value of this population is 2,500, and it says carp on my paper, so I'm assuming this is some population of carp, which I believe is a fish. There are lots of them in Lake Ontario. All right, so moving on, we're going to now find, we are now going to find, I'm not sure what we're going to find now. So I'm going to do the work for you, and then hopefully you're reading the problem and you know what is supposed to be found. T is equal to 0. I'll probably come upon it, is equal to the present time. So P of negative 10 is equal to 1,000. So I'm not sure where that came from. So I'm going to take that 1,000. I'm assuming it has something to do with the present time, though. So P of negative 10 is equal to 1,000. So we're going to take that 1,000, and we are going to set it equal to our equation. Now remember, our equation is L over 1 plus A e to the negative kt. Alright, so they want the population at times 0. The population of carp at times 0. That's what we're trying to find. Alright, so 1,000 equals L, which is 2,500, over 1 plus, we don't know what A is yet, but we do know what K is, and we do know what T is, right? T is negative 10, and so we get A e to the negative 0.25 times negative 10. And what we're trying to do here is we're trying to solve for A. So let's go ahead and do that. So we'll get 1,000 times 1 plus A e to the 2.5 equals 2,500. So 1 plus A e to the 2.5 equals 2,500 divided by 1,000, which is 2.5. So A e to the 2.5 is equal to 1.5, and then once we do that, we just say A is equal to 1.5 over e to the 2.5. So that's our A, which is equal to 0.123127. Well, A is the initial value for this function, right? So if we plug in here now, we are going to say point A, 0.123127 is equal to 2500 minus the population at time 0 divided by the population at time 0. So now what we get for that, we can now solve for our population at time 0. So we get 0.123127 is equal to times P0 is equal to 2500 minus P0. And then we just manipulate this. We'll move the P0 to the other side. We'll factor out a P0. We'll divide. And finally, we get 2,225 carp equals P sub 0. And that is it. Now, your worksheet on this is composed of all the AP problems that I currently have on the logistic equation. They are very straightforward, much more straightforward than these problems from the book, particularly since I don't see the book. So they're going to utilize those two formulas at the top of the page, particularly the one on the left here. The worksheet is 5 problems, so that's going to be your homework. This is an easy night for you. Okay, so your homework will be your worksheet. The worksheet should be in the drawer. I will show it to you. I think I have it at the bottom of my screen here, or squeen. Let's see. This is what it looks like. AP Calculus worksheet on logistic differential equations. So remember, the key is always to get it in that form where you have Kp times 1 minus 1 over L times P. There are 5 questions. I think they're all multiple choice. And most of the logistic equation problems on your AP exam will be multiple choice. So there you have it, kids. I hope you have a fabulous day, and I hope my lecture was not too horrible since I didn't have the book. It'll be the last time we struggle with this. So have a great day. Bye.